Hi everybody, welcome back to Dragonfly Engineering. So this week we're going to do a general shop kind of maintenance and UMC 750 sheet metal reassembly. So this machine I received about a month ago, and I haven't actually put the sheet metal back on the back section of it yet. There was a few things, some maintenance items that we did inside and actually started to level the machine, but you really need to do the final leveling with all the sheet metal on the back and on the top. So today we're going to do that. Yeah, so I do kind of have limited space in the shop these days with this big machine coming in. So I do have to optimize the efficiency of the shop. I think I'm going to move this manual mill over to where the lathe is currently. Let me spin the camera around. So this lathe is going to have to probably go on the other side of the EDM machine, which I'm working on as well. And then this manual mill is going to go right next to where the Haas TM1 tool room mill or CNC is going to be. That way we got, I need to have basically fire egress or exit in the shop here. So this is sort of just in the way of the general travel path here. But I think I'm going to get all of this sheet metal unpackaged and rehung on the mill, and then I'll figure out where this this mill is going to go, as well as the lathe. I don't think I'll be able to get into moving these machines in this particular episode, just because there's a lot of work involved in moving that stuff. So let's start cutting open our stack of sheet metal over here. Yeah, I'll probably arrange this sheet metal maybe out in the alleyway just to get an idea of all of the panels, and then kind of figure out how it goes onto the mill here. So let's start cutting this thing open, the pile of sheet metal that is. Okay, so we've got these fog busters, which is basically coalescing wire mesh filters, which will collect and recondense the kind of the vaporized coolant mist that exists in the mill while we're machining. And I guess you clean these like once a month or so to clean all the coolant grime out of them. So they actually added a nice little instruction sticker right on the panel. So this is panel number 1, which is this guy right there. And they kind of spell it out for you. Now, I think this UMC 750 Super Speed has additional panels on the roof, which isn't shown in this diagram. So that's probably an option that came with this mill. But I think all of the dark gray panels cover up the top axis and give clearance for the spindle head to move around, and also provide the coolant filter, which is probably sitting even on top of the extension panels that are on top of the UMC. So I'm going to start with numbers 1 through 7 and wrap the back of the machine with its white panels, starting with this panel, which is panel number 1. I have to bear with my tight camera angles. This frame is built into the machine and just flops down like that. Now there is a bunch of old aluminum dust on this mill, which I don't think is worth trying to clean off, because basically all of the wear spots that are important, it basically cleaned off with the way wipers anyway. So I'm not going to worry too much. But I may wind up with aluminum powder all over my hands. And I think right next to this mill, old number 7, there was a finishing area where everyone had these orbital sanders, and they were sanding the aluminum parts to get rid of tool marks and stuff. So these people basically are breathing in this atomized aluminum all day long, and this mill is basically covered in a film of aluminum dust. So I don't plan on that kind of practice here at this shop, mostly because I'm not running massive production. But yeah, my hands are going to have a chronic coating of gray powder from it being covering this entire mill. All right, so I guess I'll just clean the panels down after I'm done. So panel number 1 looks like it hooks onto these pan head socket cap head screws, and I think it just kind of keys in and then lays here, and then I screw them into the frame here. So let's give that a try. Yeah, so they designed in these triangular hat sections to add rigidity to the panel, but also it looks like conveniently you can lay the panel onto this welded steel tube, and it kind of keys the panel in and rests it there, so you can slide it towards the keys in the back. So that's kind of nice of them. Again, I'm here by myself today, so let's see if I can manhandle this panel up onto its roost. There we go. Alright, it looks like I need to actually take those bolts off. Yeah, unfortunately I need to take every single one of those out because there's a hose connection on this side. It almost looks like I could slide it in if I remove that hose connection. Yeah, we got that. This hose thing is preventing the sheet metal from moving far enough out to key into that socket cap head or that button head screw there. So it'd be really nice if I could just slide that in, but so I think I'm gonna unscrew that hose mount for a second so I can slide that panel over all those screw heads. Okay. Okay, let's see if I can slide these in. Okay, so I am going to try to cheat, slide this panel onto all of these screw heads. Like that. Here we go. Well, that saved a bunch of time. Now I'll just tighten one of these down so it doesn't slide off and fall off. And we should be good. I assume they designed it that way, but I wonder how many field installation people know that. All right, we got our first panel hung. Panel number 1. Now I gotta find the bag of screws that came with this thing and start tying the side panel to the framework here. All right, so I got the top bolt hangers on there. You can kind of see the clearance hole and then the teardrop shape for the bolt shank. All right, now we're ready for the top piece. This is really a two-person job, but it's just me today, so. Probably should have been done with 2 people. Alright, so I'll tighten these up. I see some more bolt holes in the front there. We're moving right along. Yeah, so this is how much coolant residue and grease is on this this machine. So I just put my hand right here, and it's just aluminum black. It's kind of covered in old coolant residue, and I saw like this goo caked on like a 1/4 inch thick around the air intakes at the top of the spindle. So I got to get up there with a scraper, a plastic scraper, and clean all that off. We do have to open up the spindle housing to replace the tool eject button. So we'll see how much goop is inside of the actual spindle assembly and around the drive motor itself. So yet to be determined, but it certainly is greasy and nasty back here. Alright. That's one. All right, so let's talk about starting up and leveling and calibrating the UMC 750 a little bit. And I'd also like to point out that I'm trying out this new Rode mic, which I'm not a sponsor of or anything. And yesterday, the receiver was slightly unplugged from the camera. So actually I was running off the camera mic, which probably sound a little distant and echoey. So if you're wondering what the audio updates or changes are, it's because I'm trying to figure out this new microphone. So anyway, let's get back to the UMC. So I did put the sheet metal on the back yesterday. There's still the sheet metal at the top to put on, but I think I'll do that in a later episode, mostly because my back is I got a little pinch probably from lifting sheet metal yesterday. But we can talk about the calibration and leveling. So I did actually do a first pass leveling of this mill, and it's kind of a tedious, boring process, so I didn't really record much of it. But we can talk about the results that we got. And it's interesting to level one of these UMCs because normally in a 3-axis mill, you just stick your level on the table and you basically adjust the jack screws under the feet until your table's level. But in a UMC, the entire table is a gimbal, so you have no reference to really level from. So I did look at Haas's website, and they talked about a procedure for leveling this mill, and they actually talked about having a special fixture that attaches or bolts to the side of the spindle of the mill itself with a X and a Y level on that. And they effectively said that you need to level your machine off of the spindle so that your spindle is absolutely perpendicular to the earth. So after you've leveled your mill based on your spindle instead of the table, then you can start to sweep with an indicator across your table and circle interpolate or do the tram testing of your table relative to the spindle itself. So Haas talks about how you need to get your frame flat by adjusting the feet, and also fix any twist in the frame of the mill through various steps of rotating the trunnion up 90 degrees and scanning across the trunnion when it's 90 degrees versus flat and everything else. And you can go to their website and see all this information yourself. It's a pretty involved set of videos and procedures. It takes several hours to go through. But we can talk about some of the highlights of this. One is that a fixture ball is used. So this is a fixture ball that comes with the mill that I purchased, and you effectively bolt this ball right onto the table's top itself. So with this ball on the table, there's a sequence that the mill goes through with the probe, and it basically probes and finds the center of the ball, and then it'll rotate the table 90 degrees and find the center of the ball again, and it's mapping where this ball is relative to the whole mill itself. And then the next thing it does is it spins the table up 90 degrees, and it goes through the sequence of probing the ball again. And by probing this ball in multiple axes or multiple orientations in the mill is mapping out exactly how this trunnion behaves relative to the ideal center defined by the touch probe itself. And then it basically recalibrates itself with a very complicated mathematical model. And I do have a video of this procedure, which I took on the cell phone, so I can show that to you now. Yeah, so after that process, which is the MRZC, I think is what it's called. I'll have to check in the mill to remember exactly what that procedure is that we just saw. But prior to running the calibration and the leveling of the mill, the first time I checked the vertical trunnion versus the horizontal trunnion, I had like a 10,000th error in positional accuracy from machining that very first part that we did, from machining horizontally and then flipping up on the side to drill the holes. The holes were off by like 10,000ths on the x-axis. So after leveling and then doing the calibration procedure we just saw, the error dropped to about 5,000ths of an inch. So I still need to probably refine the leveling of the mill some more. Again, I don't have that special level that Haas sells, or that a Haas service person would come out to install and then do a kind of a professional $2,000 or $3,000 service and installation. So I'm hoping that basically I can get it down to 1,000ths error. When the mill is in the horizontal like 3-axis configuration, currently this thing can hold 1/10 or like 2 to 3 microns accuracy, but a lot of the problem occurs when the trunnion spins up vertical. That's where kind of the accumulation of mechanical errors can kick in. So let's turn this mill on and see how things have changed after I added the sheet metal to the back. So we'll just hit the power button and it'll start up. All right, so while this controller is starting up, maybe I'll check the table again after we added maybe 600 pounds of sheet metal onto the back of the mill, and we'll see how flat we still are not. All right, so I kind of have a relatively precise level here. It's 2/10 per 10 inches, so that's 2 10,000ths of an inch over 10 inches, or approximately, what, 5 microns over 30 millimeters, or no, 30 centimeters. And right now, yeah, we're not exactly the level at the moment, even though the trunnion fundamentally tilts. I guess we do need to power up and restart and find the 0. All right. So it's doing its homing routine. And the tool changer is calibrating and finding its home location. That's what that sound is. So startup is finished. So we'll see how level we are, or the lack thereof. So put our level back on the table. Yeah, we're still off. Oh, actually not so bad. So after the mill basically homed the axes, the level is only off a little bit. So I'm going to close the door here. And this controller does give you a lot of kind of hints and suggestions, like make sure the e-stop is off. We already hit power up, and we hit cycle start to power up. So now we can hand jog if we want, so I hit the hand jog button. So we'll go to MDI, M6T7, enter cycle start. Okay, and then I will hit cycle start, and we'll go over and load tool number 7. All right, and basically I'm loading this one just so I have a something to stick the indicator on, so we can open the door now. I still got to clean the glass. There's some remnant calcium on the glass from the previous owner. Now the level was saying that this table is not totally level to earth, but I'm going to see how we're looking as far as flatness of the table relative to the spindle itself, or perpendicularity of the table. All right, so that's at 0. I'll fine tune that. Let me bring you guys in a little closer. Wow, that's as good as I can get with that lens. And then I'll jog in Y, and we'll see how we're looking. Boy, there's a lot of glare from those lights. All right, so that's 1/1000 to 0. Again, this axis can be adjusted. This is the B axis, but we are, it's moving about 1/2 thousandths that way as well, which isn't great. But again, I can change that. So if I bring the spindle all the way out, so if I bring this up, of course we got the table vise in there, so it may be limited ability for me to measure perpendicularity. But right now the mill set that at 90. Let's see if I rotate this way, reset the indicator down, change the camera location. Well, you can't see the indicator, but I'm going to sweep front to back in the 90 position. And see what we get. Again, this isn't ideal because the vise is kind of obscuring a lot of the, and then the mill doesn't want me to go down in Z anymore. It actually said restricted zone when I tried to drop in Z, because there's built-in safety guards so that you don't crash your spindle into your table when this thing is spinning around on you. But I can still drop in Z. No, it just said restricted zone that way too. So let's see if I can, no, it wouldn't let me go in Z, but I can still move in Y. But eventually it may, yeah, so if I wanted to move in Y more, I'd have to lift the Z up because it's got these built-in safety guards. All right, so I'm going to bring the spindle or the probe up to the table. And you'll have to trust me on this, but here I'm at 0. Now I'm going to sweep in Y. All right, so I'm about 0.5 thousandths off there in the back. And I was about, I don't know, 3/4 of a thousandths here. And now I'm back at 0 here. So yeah, there's apparently a lot involved with setting up the kinematic model, the mathematical model for this table, relative to how your mill sits on the floor. So yeah, to summarize the experience so far is I've attempted to tram this mill in myself using some advice from Selway Machine Tool, which is the local Haas reseller for this machine. And I actually got a quote for them to come out and kind of install the machine, which means they would level it, they'd bolt the sheet metal on and do whatever calibrations I think they would do, but it was unclear if they would do this full MRZ calibration or not. But anyway, it was going to be $2 or $3 grand, so I figured I'd give it a try myself. I mean, I can certainly put sheet metal on myself. And I tried to go through the calibration. And as I mentioned, we went from like 10 thousandths from just setting the mill on the table or on the floor to actually doing one pass at leveling and doing a self-calibration, which was that video we just saw. But I'm still seeing some errors, and the errors are mostly prominent when I actually machine a part. So this part that we have in here, let me change the camera angle. Yeah, so this test block that I've got in the vise, which is currently vertical, you can see how there's basically a profile on this edge and then another profile on this edge. So this is a notch and this is a notch. But the key is, you know, I machined these features on this facet in the horizontal orientation of the mill, and then I spun the mill up 90 degrees, and using the toolpath program, I didn't refine the corner of the part, but I was using basically the coordinate system that the mill calibrated itself to machine this tab here as well as this notch and this face. And ideally this should be exactly 1/2 inch, and then this dimension should be exactly 1/4 inch, because we're kind of machining half of this profile in a flat orientation when the table's flat, and then we bring it up 90, and we're kind of testing how accurate the mapping of this trunnion is from horizontal to vertical in a single G54 or a single work coordinate system. And what I've discovered is that effectively this dimension here is 0.505 inches, or 5 thousandths too big, whereas this pocket here is exactly 1/4 inch deep, and this pocket is exactly 1/4 inch deep relative to the faces that they machined. But this dimension is a combination of a horizontal machining and vertical machining, and I'm 5 thousandths off. And I'll bet if I sweep along there, I'm going to see a 1 thousandths deviation in the surface, similar to what I saw on the table surface itself. In fact, I know it is because I tested that off camera. So the idea is that when this mill is completely dialed, this dimension should be exactly 1/2 inch, or 0.500 inches. And right now it's 5 thousandths too thick. But I did put the sheet metal on, so maybe we should rerun this program where we machine the flat and then we machine this side and check to see if we got worse or better. So I think maybe we'll just do that now, actually. So I'll take this indicator off. I will have to get used to the door closing basically all of the time. All right, so we're gonna move up in Z. And we'll just make sure our spindle's out of the way from the table, especially in manual mode, because it's possible, I think, to actually give commands to crash your table into the spindle, even though this mill seems to have a lot of crash avoidance, hard-coded safe zones in it. All right, and then under the MDI, I'm going to tell it G0, B0, enter. All right, and hit cycle start. All right, so our B is back to 0. And I think that program is still in here. Calibration fixture. Okay, so we're going to hit cycle start. I'll turn the coolant off since we've already basically machined this. So this, again, we're rerunning this calibration program after I added all the sheet metal to the back and probably changed a little bit of the twist and the settling of the mill on the concrete floor itself. It's always good to have your finger on the feed hold button if you're just standing here watching, because you never know how you screw up. So I heard a little bit of metal get cut off there on the finish pass for that first slot. There's a little bit more skimming of that edge. Now we're going to do the 90-degree cut. All right, I heard a little bit get cut off. Huh. Uh-oh, we've got a, I think a built-in clearance problem. Potential collision detected. I think I need to shut off collision avoidance for this particular tool, because here the mill is saying that basically the spindle's getting too close to the table, because I've got this small 4-inch vise loaded on the table. Normally a 5-axis vise is a lot taller and in the center of the table, but I've got this small vise offset and it's basically encroaching on the safe zone that the mill uses to try to keep you from basically crashing the spindle into the sidewall or into the table in this 90-degree orientation. So let me turn off the collision avoidance alarm. All right, I'm back. So I found the collision avoidance setting. It's deep in the controller, but I changed that value. So let's back out of our cut here. I'm gonna lift up in Z. And then we'll just move the spindle safely out of the way, and then we'll reset the program. And we'll hit cycle start again. And so we're going to rerun the program from the start. And I'm still at, let's see, we'll go to 25% rapid. So the spindle will go to a safe location. We unlock the trunnion. We relock it, that's that air sound. And then we'll recut from the beginning of the program. Yeah, these 5-axis mills are just more involved in general. Like I mentioned earlier, when you go beyond 3-axis, the complexity goes up exponentially as far as collision avoidance and mathematical models of your table versus your spindle, the twist in the frame. It can just go on. And it can be a little bit overwhelming for a general machinist. In fact, I was just talking to my buddy, and he recommended that I actually indicate the flatness of the tool setter, which is over in the back left of the mill, because effectively the probe that you use to map out the ball location, which determines the map of the rotation of all of the axes, and that's all determined by how accurate your probe setter or your tool height setter is. So if that thing is not square, then everything that you do afterwards is going to be off, and it can throw off the map of your trunnion and everything for the proper execution of your program. All right, let's see if we have a collision problem again here. Hopefully we don't. There we go. All right, so we're cutting off more this time than we did before. I'm gonna shut off the coolant again. So I think I need to effectively do the entire calibration routine, like re-leveling, check the flatness of the tool setter, and then do the MRZP, I still may be saying that wrong, or the ball mapping and rotation mapping of the entire stage. But it sounded like, I can see we machined some material off there. And then we go back to flat. So again, the whole point of this part is to test the horizontal versus vertical repeatability of the geometry. So I'm wondering if this dimension is better now than it was previously. Well, let's test it right now. Yeah, I should use a micrometer for this, but you know, we're just kind of circling in on the target. So I'm going to use these calipers, but you can definitely machine some material off this surface. So let's see what we get. Well, 5.025. Let me find the right. All right. Well, we're 0.02 better than the last time we ran this. So that's 5.03, where this dimension should be 5. And again, this shape, this dimension is a combination of machining on this orientation and then machining on this orientation. So let's see what we are on this dimension. Here we're at 2.500, so that's good. And then for depth of that pocket, basically 250 thousandths on that pocket depth, like right on the money, to within 0.2 or so is the best I can measure with this depth indicator. Let me clean off the side over here. So adding that sheet metal and maybe just the settling of the mill a little bit more helped out with our precision from horizontal to vertical. And we're at exactly 250 depth here. So that's good. So yeah, by adding the weight to the back and maybe some more settling time, we actually shaved off another 0.02 in the air. So we're only 0.03 off on the vertical versus horizontal, which is definitely the step in the right direction. When I was looking at buying these mills, I went to a local auction and some guy was saying that the best he could ever get was 0.02 total global rotational accuracy. And I believe he was saying total internal runout, so plus or minus 1,000. But I want to see exactly how good we can get this without having to cheat, and basically when this stock is in vertical position, reprobe and have a different work offset. That's kind of like a way of cheating, but we may have to do that for some mill setups until ultimately we need to do full fluid 5-axis simultaneous machining, in which case the tricks of or setting your work coordinate to G55, which is opposed to G54, on different orientations of your part is basically cheating. So we don't want to do that. So yeah, we went from 0.10 down to 0.03 by doing a first pass horizontal or a first pass leveling of the machine, and by adding the sheet metal and then doing our amateur tramming and twist setup for the frame of this machine, and our amateur MRZP calibration using that ball reference. So yeah, we're definitely moving in the right direction. Yeah, so I think the next step is I'm going to indicate the flatness of that tool setter right there. And if this surface is not exactly perpendicular to the spindle, then when we come in and we set the probe height, or there's a reference tool holder that came with this mill that is effectively exactly 5 inches. But if we, and that 5-inch length is then used to calibrate the probe itself, which is used to map out the rest of the your stock as well as the table and all of that, using the reference ball. But if our initial calibration of the touch probe is off because this surface isn't totally perpendicular, then that will throw off everything downstream of the touch probe. This machine actually has an extra pump on the side. Let's go and take a look. Yeah, so we got this extra pump right here, and this is like a high pressure pump that will spray high pressure coolant through the center of the spindle itself and through the tool holder, and ultimately through little spiral holes in the end of a through coolant spindle tool, like a drill bit, or I think some end mills have coolant nozzles at the tip of the end mill itself. It's mostly helpful for deep drilling so that you don't have to drill peck. In fact, you can just have high pressure coolant right at the cut edge at the end of your drill, and it blows all the chips out the back. Another nice thing of the high pressure coolant is that you can use it for, or I'm going to attempt to use it to clear chips, or actually spray down your machined part at the end of a run. So let's see if I can find the tool holder that has a hollow pull stud, and I can demonstrate the through coolant spindle spray. And then there's a hole in this pull stud, and in that hole, high pressure coolant flows from the center of the spindle through the tool holder and out the bottom. And this is basically the fire hose tool that I currently have. So I can demonstrate my theoretical utility of through coolant, or through tools coolant. So if we've got, chips all over our part like that, I'm definitely going to close the door on this one. Some CNC accessories are that you can buy a little fan that you do a tool change with a tool that's got like model airplane propeller fan blades on it. But when you've got through spindle coolant, you can do a little bit more of an aggressive chip clearance. So I'm going to hit auxiliary coolant, and then we can blast it just like that. And then we can move around and completely clear out all of the crap on our part. And then you got to let it finish and then drain. And there you go. We've got no more chips on our part. Isn't that nice? I think that's a little more effective. But you do have to make sure that you have a through spindle coolant tool and a through spindle coolant pull stud on the back of your tool holder. Otherwise, you're going to pressurize the crap out of your spindle, and the mill won't let you release your tool for probably 3 or 4 hours as the pressure slowly drops inside of your spindle column. Or, if you actually somehow overcome that and you release the tool, it may shoot the tool out of your spindle because there's so much liquid pressure behind that pull stud.